Welcome to this walkthrough of LeetCode problem number 1369. Get the exact data from LeetCode for problem 1369. In this session, we'll explore the problem, break down possible approaches, and highlight key strategies for solving it. Let's dive in. I am unable to provide the exact problem statement for LeetCode problem number 1369 as it requires direct access to LeetCode's platform, which I cannot retrieve. If you can share the problem details or context, I can assist by creating detailed explanations, examples, or solutions for you. When tackling a LeetCode problem, it's often helpful to start by considering a brute force approach. This is the most straightforward way to solve the problem because it involves directly implementing the logic based on the problem description. For example, you might iterate over all possible combinations or permutations of the input to find the solution. While this method is simple to understand and implement, it is usually inefficient for larger inputs due to its high time complexity, which is often n squared, or worse. The trade-off is that brute force solutions are a great way to validate your understanding of the problem and ensure correctness, even if they are not practical for competitive programming. By starting with brute force, you can lay a solid foundation before moving on to more advanced techniques. Now, to make your solution more efficient, you should analyze the problem for patterns or redundancies that can be eliminated. An optimized approach often involves leveraging specific data structures or algorithms to reduce time complexity. For example, hash maps can provide constant time lookups, while sorting can help reduce the problem space for certain tasks. You might also use mathematical properties or apply well-known techniques like binary search, sliding window, or dynamic programming. While these methods often bring the time complexity down to n log n, or even n, they require a deeper understanding of the problem and more careful implementation. Additionally, alternative strategies like divide and conquer, greedy algorithms, or dynamic programming may suit particular problem types. These techniques break the problem into smaller pieces, simplify decision-making, or reuse results to optimize performance. Each of these approaches has its own set of trade-offs, so it's essential to weigh their pros and cons carefully. Once you've explored different techniques, determining the most suitable strategy depends on the specifics of the problem. For smaller inputs, brute force is often a good starting point to validate your solution and gain insights into the problem. However, for larger inputs, you'll want to analyze constraints and look for patterns that can make your solution more efficient. It's also important to assess trade-offs, like whether a more optimized approach might increase the complexity of your code. Key observations, like identifying edge cases or recognizing hidden patterns in the input, often lead to the aha moment where the solution strategy becomes clear. For example, noticing symmetry or some mathematical property in the data can open the door to a highly efficient solution. Ultimately, the goal is to balance efficiency with clarity, ensuring that your solution is both correct and scalable. In deciding the best approach, understanding the trade-offs is crucial. Brute force solutions are simple to implement but often too slow for large inputs. Optimized solutions, on the other hand, are faster and more scalable but can involve more complex code, which increases the risk of bugs. Strategies like divide and conquer or dynamic programming are powerful tools for many problems but require a detailed analysis of the problem structure and careful implementation to avoid mistakes. Ultimately, the key to selecting the best approach lies in thoroughly analyzing the problem's constraints, input size, and properties. By doing so, you can identify the most efficient and practical solution while minimizing the trade-offs in both time and space complexity. To solve any algorithmic problem effectively, the first step is to fully understand the problem statement. This means reading the description carefully to identify the input, the expected output, and any constraints provided. For instance, are you working with arrays, strings, or graphs? What is the format of the output, an integer, a boolean, or a list? It's also important to identify what the problem requires you to do, such as finding a pattern, performing a calculation, or transforming data in a specific way. Once you have clarity on these aspects, the next step is to analyze the nature of the input and output. This includes defining their structure, accounting for edge cases like empty inputs or extreme values, and ensuring your solution handles these scenarios properly. After that, you should select an appropriate approach. Sometimes a brute force method might suffice, but in many cases, optimization is needed. This is where identifying key algorithms or techniques, such as dynamic programming or binary search, can make a big difference. Finally, planning the algorithm is crucial. Break the solution into small, manageable steps and visualize how the data flows through each step to ensure a clear and logical process. As part of the planning phase, it's also important to consider the time complexity of your algorithm and strive for the most efficient solution possible within the constraints. Once the plan is clear, you can move on to implementing the solution. This involves choosing the right data structures, such as arrays for sequential data, hash maps for quick lookups, or heaps for priority-based operations. Writing clean and modular code is equally important, with comments to explain the key steps for better readability and maintainability. After the implementation, testing the solution thoroughly is a critical step. Start with simple test cases to confirm that your solution works as expected. Then, include edge cases, such as the smallest and largest inputs or unusual scenarios, to verify robustness. Cross-checking the outputs against the expected results ensures correctness. Along the way, some key insights can improve your problem-solving process. Recognizing patterns in the data, such as subarrays or connected components, can lead to efficient solutions. Optimization techniques, like memoization or dynamic programming, help eliminate redundant computations. Always account for edge cases and aim for the most efficient solution in terms of time complexity, such as O, n, or O, n log n, depending on the problem's requirements. To solve algorithmic problems efficiently, understanding the role of data structures is essential. Arrays, for example, are often used for sequential data and allow constant time access to elements. Hash maps are invaluable for tasks like counting frequencies or mapping relationships, as they provide fast lookups. Heaps are particularly useful for retrieving minimum or maximum elements based on priority, and graphs represent connections or relationships, making them ideal for traversal algorithms like BFS and DFS. Let's apply these principles to a hypothetical problem, finding the single non-duplicate element in a sorted array where every other element appears twice. A binary search approach can solve this problem efficiently in O log n time. The key observation here is that in a sorted array, duplicate pairs are always split between the left and right halves of the array. By leveraging this property, we can systematically narrow down the search space to locate the non-duplicate element. To solve the problem, we start by initializing two pointers, low and high, at the beginning and end of the array, respectively. Next, we calculate the middle index, mid, and ensure that it is even. If not, we adjust it. This ensures we always compare pairs correctly. Now, compare the element at mid with the one immediately following it. If these two elements are equal, it means the non-duplicate element lies in the right half of the array, so we adjust low to mid plus 2. Otherwise, it lies in the left half, so we move high to mid. This process continues until the low and high pointers converge, at which point the element at low is the single non-duplicate element. The provided Python code demonstrates this process step by step. It efficiently reduces the search space with each iteration, ensuring that the solution is both fast and correct. The binary search approach relies on two key operations, narrowing down the search space and adjusting the middle index to ensure even positions are compared. These operations allow us to systematically identify the non-duplicate element. In terms of complexity, the time complexity is O log n, because the search space is halved with each iteration. The space complexity is O(1), since no additional data structures are used. When solving this problem, it is important to consider edge cases, such as arrays with only one element or cases where the non-duplicate element appears at the beginning or end of the array. Overall, this problem highlights the power of binary search for efficiently solving problems involving sorted data. By carefully adjusting the middle index and leveraging the properties of the data structure, we achieve an optimal solution that is both efficient and robust. This code is a placeholder template for LeetCode problem number 1369. It defines a class solution with a method example underscore function to perform a basic operation on a list of numbers, e.g., squaring each number. The example demonstrates how to use the class and function, with a sample input, 1, 2, 3, 4, which returns 1, 4, 9, 16. Once the problem requirements for LeetCode number 1369 are known, replace the logic inside example underscore function with the actual solution. This is the Java implementation of the placeholder logic for LeetCode problem number 1369. It mirrors the provided Python implementation, where the function squares each number in an input array. Key differences include using Java's list4 dynamic storage, explicit type declarations, and a main method for demonstration. The example function method iterates over an array of integers, squares each value, and stores the results in a list, which is then returned. Here, we start with the input list 1, 2, 3, 4. Initially, the result list is empty. In the first iteration, we take the first element from nums, which is 1. We compute its square, 1 * 1, which equals 1, and append it to the result list. Now, the result contains 1. In the second iteration, the next number is 2. We calculate 2 * 2, which equals 4, and add it to the result. The result list now becomes 1, 4. In the third iteration, we proceed with the number 3. Squaring it gives 3 * 3 equals 9. This value is appended to the result, updating it to 1, 4, 9. Moving to the fourth and final iteration, the number is 4. Its square, 4 * 4, equals 16. We append 16 to the result, resulting in 1, 4, 9, 16. With all elements processed, the final output for this example is 1, 4, 9, 16. Now, we look at a new example with the input list, -1, -2, -3, -4. The result list begins empty again. In the first iteration, we take the first number, -1, and compute its square. Multiplying -1 by itself gives 1, which we append to the result. The list becomes 1. In the second iteration, the next number is -2. Squaring it results in 4, which is added to the result, updating it to 1, 4. Continuing with the third iteration, the number is -3. Calculating its square gives -3 * -3 equals 9. We append this value to the result, resulting in 1, 4, 9. In the fourth iteration, the final number is -4. Its square, -4 * -4 equals 16. Adding this to the result list gives 1, 4, 9, 16. The process ends here, and the final output for this example is 1, 4, 9, 16. In this example, the input list is 0, 5, 10. Starting with an empty result list, we process the first number, 0. Squaring it results in 0 * 0 equals 0. We append this value to the result, which now holds 0. In the second iteration, the number is 5. Its square, 5 * 5, equals 25. Adding this value updates the result to 0, 25. For the third and final iteration, the number is 10. Squaring it gives 10 * 10 equals 100. Appending this value to the result results in 0, 25, 100. With all elements processed, the final output for this example is 0, 25, 100. To summarize, the algorithm squares each number in the input list and appends it to the result. This method is efficient, with O(n) time complexity since it processes each element once, and O(n) space complexity due to the storage of the result list. To analyze the time complexity of the given Python function, we start by considering the for loop that iterates over the input list nums. If the list contains n elements, the loop will execute exactly n times, which contributes O(n) to the overall time complexity. Within each iteration, the operation number * number computes the square of the current element. This is a constant time operation, or O(1), and since it occurs once per iteration, its contribution over n iterations is O(n) *O(1), which simplifies to O(n). Lastly, the append operation adds the squared value to the result list. In Python, appending to a list is an amortized O(1) operation. Repeated over n iterations, this also contributes O(n) to the overall time complexity. Together, these components form the basis of our time complexity analysis. Now, summing up all the contributions to the time complexity, we have O(n) for the iteration, O(n) for squaring each element, and O(n) for appending results to the result list. Therefore, the total time complexity of the function is O(n). Shifting to the space complexity, the input list nums remains unmodified throughout the function, so it does not add to the space complexity. The result list, which stores the squared values, requires additional space proportional to the size of the input list. Since there are n elements to store, this contributes O(n). Lastly, the temporary variables used in the loop, such as number and the intermediate results of number ** number, occupy constant space, or O(1). These are the main components we consider for calculating the space complexity. When we evaluate the total space complexity, the dominant factor is the space required for the output list result, which scales with the size of the input. This means the overall space complexity is O(n). Comparing this approach to a brute force method, such as creating multiple intermediate lists or resizing the output list inefficiently, we observe that the current implementation minimizes memory overhead and processes each element in a single pass. While the time complexity would still be O(n), in a brute force scenario, the constant factors could increase significantly due to redundant operations. Finally, analyzing the best, average, and worst case scenarios, we see that the complexity remains O(n) across all cases. This is because the algorithm processes every element of the input list exactly once, regardless of the input's properties. This single-pass, linear approach ensures optimal performance for both time and space. When tackling coding problems, there are several common mistakes that can hinder your progress. First, a frequent issue is misunderstanding the problem statement. It's easy to dive into coding without fully grasping the requirements, but this can lead to incorrect assumptions about the input size, constraints, or edge cases. Always take the time to carefully read and clarify the problem before starting. Another key mistake is ignoring edge cases. For example, scenarios like empty inputs, single-element arrays, or maximum constraint values often trip up solutions. Testing your code with a variety of examples can help you avoid these pitfalls. Additionally, using an inefficient approach, such as brute force or algorithms with high time complexity, might pass small test cases but fail when inputs scale up. Be mindful of optimizing for both time and space complexity. Loop errors, like off-by-one mistakes in conditions, are also common and can lead to runtime issues. To mitigate this, use clear variable names and thoroughly test boundary conditions. Lastly, overcomplicating the solution can make debugging harder and introduce inefficiencies. Many problems have elegant solutions, so look for patterns or properties like bit manipulation or prefix sums to simplify your approach. Now, let's focus on insights you can apply during interviews. Recognizing patterns is crucial since many problems are variations of classic techniques like sliding windows, dynamic programming, or graph traversal. Identifying the underlying pattern early can save you time and effort. It's also important to communicate your thought process clearly. Explaining your steps before coding demonstrates your problem-solving skills and allows the interviewer to provide helpful guidance if needed. A good strategy is to optimize incrementally. Start with a brute force solution to establish correctness, then refine your approach step by step. This progression is something interviewers value. Additionally, always dry run your code with a simple test case to catch any logical errors before you submit. For practice, consider exploring related problems such as LeetCode 136, which focuses on bit manipulation, or LeetCode 560 and 494 for prefix sums and dynamic programming, respectively. Each of these provides valuable opportunities to strengthen your understanding of core concepts. Finally, let's talk about alternative approaches and important trade-offs. Brute force solutions can be useful for small input sizes, as they're straightforward and help you understand the problem. However, they're generally inefficient for larger datasets. Optimized solutions often leverage techniques like hashing, sorting, or binary search. For instance, using a hash map can reduce a naive O(n) solution to O(n), which is a significant improvement. Depending on the problem, specialized techniques such as dynamic programming, greedy algorithms, or graph-based methods may be necessary, but each comes with trade-offs. It's important to weigh these carefully. For example, optimizing time complexity often requires additional space, like using hash maps, so always consider the memory constraints of your problem. Similarly, while an efficient solution may perform better, it might also be more complex to implement and debug. Strive for a balance between simplicity and performance that aligns with the problem's requirements and your familiarity with the techniques involved. Thanks for following along. We've touched on the key aspects of LeetCode problem number 1369. Remember to practice consistently and tackle similar problems to refine your skills. Don't forget to like, share, and subscribe for more content. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!